Find somewhere comfortable. You don't need to follow any of this closely. You don't need to remember a single thing that's said tonight. Just let the words come and let them drift past you, the way light moves through a quiet room. We're going nowhere in particular. We're in no hurry at all. If today was hard, and for a lot of people, today was hard, you can set it down now. Whatever you carried through the hours, whatever is still turning over somewhere in the back of your mind, it doesn't need your attention tonight. The day is already behind you. The dark is already here, and the dark is patient. Tonight we're going to follow a very small thing. Something so small it has no color, no weight, no size you could ever measure with any instrument you could hold in your hand. We're going to follow an electron, one of the tiny particles that circles the heart of every atom in everything you've ever touched. As it falls, just falls, one small drop from one level to another, inside an atom too small to imagine. And from that fall, a single particle of light is born, one photon, one color. We're going to follow that color from a darkened room in 17th century England through the puzzles of 19th century scientists into the heart of the sun and back again to the lamp beside your bed. You don't need to understand every word, just let it arrive softly, the way the best things do. We'll begin in the dark. It was the summer of 1666, and England was still recovering from plague. Isaac Newton, 23 years old and already quietly extraordinary, had retreated from Cambridge to his family home in Lincolnshire, Woolsthorpe Manor, a modest farmhouse with thick stone walls and low ceilings and, in one of its rooms, a single small window that faced the afternoon sun. He had a glass prism, a triangular wedge of polished glass, the kind that lens grinders and opticians kept as curiosities. And in that room he did something that sounds almost too simple to matter. He blocked the window almost entirely, leaving only the narrowest gap so that a single thin blade of sunlight cut across the dim air and fell upon the prism. What came out the other side was a ribbon of color across the wall, red, then orange, then yellow, then green, then blue, then a deep and quiet violet, the spectrum. The full arc of visible light laid out in order, each shade bleeding into the next. This was not entirely new. People had seen rainbows for as long as there had been people to see them. Glass prisms had scattered light into color before. But Newton did something careful and methodical that no one before him had quite done. He asked what the colors meant. He didn't assume the prism was adding color to the light, staining it somehow, the way a tinted glass might tint water. He suspected the opposite. He suspected the colors were already there, hidden inside the white light, and the prism was simply pulling them apart. To test this, he let the spectrum fall onto a second prism, oriented the opposite way, and the colors recombined. White light came out the other side, clean and clear. The prism hadn't made the colors, it had revealed them. White light, it turned out, was not a single pure thing. It was a mixture, a chord of many notes, all arriving together, indistinguishable until something separated them by their nature. The nature in question was wavelength. Light, we now understand, is a wave, a ripple in the electromagnetic field that fills all of space. Different colors of light correspond to different wavelengths of that ripple. Red light has a longer wavelength, somewhere around 650 to 700 nanometers, a nanometer being 1/1000th of a meter, a unit so small it's easier to feel than to picture. Violet light has a shorter wavelength, somewhere around 400 nanometers. When light travels through glass, different wavelengths bend by slightly different amounts, and so the prism peels them apart, spreading them across the wall in the order of their wavelengths, from long to short, red to violet. Newton called this the spectrum, from the Latin word for appearance or image or ghost. It was a good word for it. There was something slightly haunting about the sight. All those colors that had been riding together invisibly through space, suddenly made visible, suddenly separated and named. But the question Newton's experiment raised was deeper than anything his prism could answer. Yes, white light was a mixture. Yes, different colors had different wavelengths. But why? Why did light come in different wavelengths at all? Why, when you heated a piece of iron until it glowed, did it glow first red, then orange, then yellow, and never violet first? Why did different substances, when burned, produce different colors of flame? Why did the sky scatter blue and not green? Why did the sunset run red and orange and not the cooler end of the spectrum? Newton didn't know. He was 23. And he had made one of the most important discoveries in the history of optics, and he was still standing at the threshold of something vast. The prism had opened a door, but the room beyond it was dark. That room would take another 2 centuries to properly illuminate. For now, picture it, a quiet stone farmhouse in Lincolnshire, summer light pressing through a crack in the shutters, a young man watching a band of colour move slowly across the wall as the afternoon turned. The colours are there. They have always been there. They are waiting, with the patience of very old things to be understood. Colour was one mystery, but hidden inside it was a stranger one. In 1802, a British chemist and physicist named William Hyde Wollaston was doing what scientists of his era often did, trying to improve on an existing technique. He was examining the solar spectrum. Sunlight passed through a narrow slit and then through a prism, and he noticed something that didn't fit. Running across the rainbow of color at specific places were thin, dark lines, not smudges or shadows. Precise, narrow, definite gaps, as though certain specific colors had simply been removed from the light. He noted them. He published a brief account, and then, with the particular blindness that sometimes afflicts even careful observers, he assumed they were simply the natural boundaries between colors, the dividing lines between red and orange, orange and yellow, and thought no more about it. He was wrong, and it would take a young German glassmaker to prove it. Joseph von Fraunhofer was born in 1787 in Straubing, Bavaria, the 11th child of a master glazier. He was orphaned at 11, apprenticed to a glassmaker in Munich, and by all accounts should have lived and died in obscurity, grinding lenses for spectacles and telescopes. But he had an extraordinary eye and a ferocious precision, and he became obsessed with understanding the optical properties of glass, not just practically, but in detail. He needed to know exactly how much light bent when it passed through different kinds of glass at different wavelengths, because only then could he grind lenses that were truly free of color distortion. To measure this, he needed a reliable source of light at known wavelengths. He turned to the solar spectrum. And when he looked at it with instruments far more refined than Wollaston's, what he saw stopped him. Not a few dark lines, hundreds of them. By 1814 he had catalogued more than 570, and he mapped them with extraordinary care, assigning letters to the most prominent ones. The A line near the red end, the D lines in the yellow, the H lines near the violet. He published his findings, and the scientific world was quietly astonished. These lines, which now bear his name, the Fraunhofer lines, were not boundaries between colors. They were something else entirely, specific wavelengths of light precisely removed from the continuous spectrum, present in every observation of sunlight, always in exactly the same positions, always the same width, always the same darkness. Fraunhofer could measure them with extraordinary precision. He could not explain them at all. They were a code he had no key to read. Meanwhile, something else was being noticed in a completely different context. In 1826, a Scottish scientist named William Henry Fox Talbot, the same man who would later go on to invent one of the earliest photographic processes, was studying the colors produced by burning different chemical salts in a flame. He found that if you sprinkled a lithium compound into a Bunsen flame, it burned red. A copper salt burned blue-green. Strontium burned a brilliant crimson. And sodium, ordinary table salt, burned a vivid, intense yellow, so bright it could overwhelm everything else in the flame. Talbot noticed something important. These colors were not just roughly different, they were precisely different. Each element had its own shade, and that shade was always the same, regardless of what compound the element was in, regardless of the temperature of the flame within a reasonable range. He wrote that the colors could be used to identify the chemical elements present in a substance, the way a face identifies a person. It was a clue. It was perhaps the most important clue in the history of chemistry. But Talbot, like Wollaston, like Fraunhofer, was standing in front of a door he didn't yet have the key to open. What was removing those specific wavelengths from sunlight? Why did each element burn in its own particular color? What was the connection between the dark lines in the sun's spectrum and the bright colors in a flame? The two observations sat apart, apparently unrelated, for another 3 decades. Fraunhofer's dark lines on one side, Talbot's colored flames on the other, and somewhere between them, a pattern waiting patiently to be seen. It is one of the gentle ironies of science that the answers to the oldest questions sometimes wait, not for new instruments or new data, but simply for someone to look at what is already there from a slightly different angle. All the evidence was present. The picture was already painted. It only needed the right eyes to see it whole. Heidelberg in 1859 was a university town of particular beauty, the old city climbing the hillside above the Neckar River, the ruined castle looking down from the ridge, the streets full of students and professors, and the particular quiet industriousness of a place devoted to learning. It was here, in a laboratory that smelled of gas and heated metal, that 2 scientists built an instrument and changed the course of chemistry. Gustav Kirchhoff was a physicist, precise and methodical, with a gift for finding deep principles buried inside apparently unrelated observations. Robert Bunsen was a chemist, famous today for the burner that bears his name, though he would have found that particular legacy slightly reductive, since his real work ranged far more widely. Bunsen was warm and generous, a beloved teacher, and by the time Kirchhoff arrived in Heidelberg as a professor, the 2 men had already become close friends. Their collaboration was one of those rare partnerships where different kinds of intelligence meet and produce something neither could have reached alone. What they built together was called a flame spectroscope. It was not, in principle, complicated. A small flame at one end, Bunsen's burner burning clean and nearly colorless so as not to contaminate the results. A narrow slit for the light to pass through, a collimating lens which turned the diverging rays of light into a parallel beam, a prism to separate the wavelengths, and a small telescope at the other end through which an observer could examine the resulting spectrum with great precision. When you placed a substance in the flame and looked through the telescope, you didn't see a rainbow. You saw something much more specific, a series of bright colored lines against a dark background. Each line was a precise wavelength of light. Each line had a precise position in the spectrum. And the pattern of lines, the number of them, their colors, their spacing, was completely unique to the element burning in the flame. Sodium produced 2 bright yellow lines, sitting so close together they sometimes appeared as one. The same yellow Talbot had noticed, now resolved into its precise nature. Potassium gave a violet line and a red one. Lithium gave a brilliant crimson. Strontium gave a richer set of lines, spread across the red and orange. Each element had its own pattern, as individual and unmistakable as a fingerprint. Kirchhoff and Bunsen immediately understood the power of what they were seeing. If each element had a unique spectral signature, then spectroscopy, the analysis of these patterns, could be used to identify elements in any mixture, however complex, however small the sample. Chemistry had previously relied on reactions. You added one substance to another and watched what happened. Spectroscopy required only light. You could identify an element from across a room. You could, in principle, identify it from much farther away than that. They turned this new tool on a sample of mineral water from a spring near Durkheim. The water was known to contain various salts, and they expected to find the usual suspects: sodium, potassium, calcium. But among the familiar lines, they found 2 blue lines that matched nothing in their reference collection, nothing known. Kirchhoff and Bunsen named the unknown element cesium, from the Latin for sky blue, after the color of its most prominent spectral lines. It was discovered not by any chemical reaction, not by any physical separation, but purely by the color of its light. A year later, examining the residue of 40 tons of mineral water that had been evaporated down, they found another new element, this one producing deep red spectral lines. They named it rubidium, from the Latin for deep red. 2 new elements found by color alone. Then Kirchhoff turned his spectroscope toward the sun. He remembered Fraunhofer's dark lines, those precise, unexplained gaps in the solar spectrum, and he noticed something that must have produced a moment of quiet, electric clarity. The positions of Fraunhofer's dark lines matched exactly the positions of the bright emission lines he was seeing from heated elements in his laboratory. The dark D lines in the solar spectrum sat at precisely the same wavelengths as the bright yellow lines of sodium. He worked out what this meant, and the explanation was as elegant as anything in 19th century science. The sun's interior was intensely hot, hot enough to emit a continuous spectrum of light across all wavelengths, a smooth, unbroken rainbow. But the sun's outer atmosphere was cooler, and it contained sodium, and when the continuous light from the interior passed through this cooler outer layer, the sodium atoms there absorbed the exact same wavelengths they would otherwise emit. They swallowed those specific wavelengths out of the passing light and left dark gaps in their place. It was the same phenomenon seen from 2 directions. In the laboratory, a hot gas emitting bright lines at characteristic wavelengths. In the sun, a cool gas absorbing those same wavelengths from the light passing through it. Emission and absorption, 2 faces of the same process. Fraunhofer's dark lines were not a mystery anymore. They were a catalogue. They were the sun's own spectral fingerprint, written in absence rather than in light. Every dark line was the signature of an element in the sun's atmosphere, absorbing the wavelengths that were its own. The sun was telling anyone who cared to listen exactly what it was made of. It had been telling them for as long as there had been sunlight. Kirchhoff and Bunsen had learned to listen. What they could not yet explain was why. Why did each element have its own particular set of lines? Why those wavelengths and not others? Why did the pattern stay constant, regardless of how hot the flame or how bright the source? The fingerprint was real and reliable and extraordinarily useful. But its origin, what was happening inside the atom to produce it, would remain unknown for another 50 years. That explanation, when it came, would be one of the most beautiful in all of science. In 1885, a Swiss mathematics teacher named Johann Jakob Balmer sat down with Fraunhofer's measurements of hydrogen's spectral lines and did what mathematicians do when faced with a sequence of numbers. He looked for a pattern. Hydrogen was the simplest element, the lightest, the most abundant in the universe, and the one with the fewest and cleanest spectral lines. In the visible part of its spectrum, hydrogen produced 4 distinct lines: a red line, a blue-green line, a blue line, and a violet line. Their wavelengths had been measured precisely, and Balmer found that they fitted a remarkably simple formula, a pattern involving whole numbers, squares of whole numbers, and a single constant that seemed to have no obvious physical meaning. He published his formula, and it worked. It predicted the wavelengths of those 4 visible lines with extraordinary accuracy. It also predicted lines beyond the visible range, in the ultraviolet. that were later found to exist exactly where he said they would. It was one of those moments in science where a pattern is so clean, so precise, so obviously not a coincidence that you know it must mean something deep. But Balmer himself didn't know what it meant. He had found the pattern. The explanation was still hidden. The explanation came in 1913 from a young Danish physicist named Niels Bohr, and it required a completely new way of thinking about the atom. By 1913, scientists already knew that atoms had a structure. Ernest Rutherford had shown, in a famous experiment involving gold foil and a beam of particles, that almost all of an atom's mass was concentrated in a tiny central nucleus, and that electrons, much lighter, negatively charged, orbited this nucleus at a relatively vast distance. An atom was mostly empty space, with a dense kernel at the center and electrons moving somewhere in the surrounding void. But this picture had a problem. According to the physics of the time, an electron moving in a curved orbit should be constantly radiating energy. It should be spiraling inward, losing energy continuously and crashing into the nucleus within a fraction of a second. Atoms should collapse almost instantly. Clearly they didn't. Clearly something was wrong with the picture. Bohr proposed something that was, at the time, frankly radical. He said that electrons didn't orbit just anywhere. They could only exist in certain specific orbits, corresponding to specific, fixed amounts of energy. Not a continuous range of possibilities, but a set of distinct, allowed values, like the rungs of a staircase, where you can stand on the first step or the second or the third, but not on the smooth slope between them. Each rung had a precise energy associated with it. An electron on the lowest rung was in its most stable state, what physicists call the ground state. An electron could be pushed to a higher rung if it absorbed exactly the right amount of energy, no more, no less. And here was the crucial part. An electron on a higher rung was unstable. It would fall back down, sooner or later, to a lower rung. And when it fell, the energy it released didn't vanish. It couldn't vanish. Energy doesn't disappear. Instead, it was emitted as a single photon of light, a single particle wave of electromagnetic energy, carrying away exactly the difference in energy between the two rungs. The color of that photon, its wavelength, was determined entirely by the size of that energy difference. A large drop from a high rung to a low one released a high energy photon, blue or violet light, short wavelengths. A smaller drop released a lower energy photon, red light, long wavelengths. The precise wavelength of each emitted photon corresponded exactly to a precise energy difference between two specific rungs on the atom staircase. And this explained Balmer's formula. The 4 visible lines of hydrogen corresponded to 4 specific electron transitions, electrons falling from the 3rd, 4th, 5th, and 6th rungs down to the 2nd rung. Each fall released a photon of a specific energy and therefore a specific wavelength. The red line was the smallest of these falls from the 3rd rung to the 2nd. The violet line was the largest from the 6th rung to the 2nd. Balmer's mysterious constant, the number that made his formula work without anyone knowing why, turned out to encode the energy of hydrogen's 2nd rung. The mathematics that had seemed arbitrary was actually a map of the atom's interior. It is worth pausing on how strange this is and how wonderful. The colors of hydrogen's light were not random. They were not a continuous smear. They were 4 precise lines because there were 4 specific drops available to hydrogen's electron as it fell toward its lowest rung, and each drop had a precise size, and each size corresponded to a precise color. The color was the record of the fall. Bohr's model wasn't the final word. The full story of quantum mechanics, which came in the 1920s, showed that electrons don't orbit in the simple circular paths he imagined, but exist instead in probability clouds, regions of space where they are more or less likely to be found at any moment. The staircase picture is a simplification of something more intricate and more strange, but the essential insight survives. Electrons in atoms can only hold certain amounts of energy, and when they move from one allowed energy level to another, they emit or absorb photons whose energy matches the gap exactly. The staircase is real. The colors are the sound of electrons descending it. For hydrogen, with its single electron and single proton, the staircase is clean and simple and perfectly calculated. It was the ideal atom to start with, nature's own worked example, left out for anyone patient enough to study it. And the pattern it revealed turned out to be universal, written into the structure of every atom in the universe, each one with its own staircase, its own set of rungs, its own characteristic colors. Hydrogen was the beginning, but there are 94 naturally occurring elements in the universe, and each one glows differently. The reason begins with the nucleus. Every atom has a nucleus made of protons, positively charged particles, and neutrons which have no charge. Hydrogen has 1 proton, helium has 2, lithium has 3, carbon has 6, iron has 26. The number of protons in the nucleus is what defines an element. Change the proton count, and you change the element entirely. And because the nucleus is positively charged, it holds on to the negatively charged electrons that surround it, and the more protons there are, the stronger that pull, and the more electrons are needed to balance it. So each element has a different number of electrons arranged around its nucleus, and those electrons don't all crowd into the same space. They arrange themselves in shells, the first shell holding at most 2 electrons, the second holding up to 8, the third up to 18, and so on, with each shell corresponding to a different range of energies, and within each shell, different sublevels with their own distinct energies. The precise energy of each level, each rung on the staircase, depends on the electrical balance between the nucleus and the electrons. It depends on how many protons are pulling inward and how many electrons are pushing outward against each other. Every element has a different number of each, and so every element has a different arrangement of energy levels with different gaps between them. No 2 elements share the same staircase. No 2 elements share the same set of spectral lines. Think about sodium for a moment. Sodium has 11 protons and 11 electrons. Its outermost electron, the one most loosely held, the one farthest from the nucleus, sits in a particular energy level that is very specific to sodium's particular electrical balance. When that outer electron is given a little energy, say by being placed in a hot flame, it jumps to a higher level. And when it falls back, it releases a photon at a wavelength of about 589 nanometers. That wavelength sits in the yellow part of the visible spectrum, and it is so intense, so bright, so dominant in sodium's emission that sodium light is practically synonymous with yellow. The sodium vapor lamps that used to line city streets at night, the ones that turned everything, a warm amber and made the world look slightly like a sepia photograph. Those were running on exactly this transition, 1 electron in one kind of atom, falling one particular distance and releasing one particular color, over and over and over, millions of times a second, filling the street with yellow. Over and over and over, millions of times a second, filling the street with yellow. Strontium is different. Strontium has 38 protons and 38 electrons, and its energy levels are spaced differently, and when its electrons fall, they release photons in the deep red around 650 to 700 nanometers. The pyrotechnic chemist who loads a shell with strontium carbonate or strontium nitrate is, without perhaps thinking of it this way, arranging for millions of strontium electrons to be energized simultaneously by the heat of the explosion, and then to fall back to their ground states in the brief, bright moment of the burst, each one releasing a red photon, and the collective result being that streak of vivid crimson against the dark sky. Copper produces a blue-green color somewhere around 480 to 500 nanometers, which is why copper compounds are used for the blue and teal effects in fireworks. Barium gives a bright green at around 550 nanometers. Cesium, The element Kirchhoff and Bunsen found by its spectral lines produces a beautiful blue-violet. Potassium gives a pale violet, and sodium, as we've said, overwhelms everything with yellow, which is why fireworks manufacturers have to be careful about sodium contamination in other colors. Even tiny amounts of sodium can muddy a red or a green with yellow light. A fireworks display is, in a sense, an accidental demonstration of atomic physics written across the night sky. Every burst is a collection of electron transitions, happening simultaneously in millions of atoms, each element contributing its own precise color to the overall picture. The colors are not chosen arbitrarily. They cannot be adjusted or tweaked. They are fixed by the laws of quantum mechanics, by the spacing of energy levels in each particular nucleus and electron system, by the same physics that governs hydrogen's 4 lines and the Fraunhofer lines in the sun. For elements with many electrons, the situation becomes considerably more complex and considerably richer. When an atom has dozens of electrons, those electrons interact with each other. They push and pull and partially screen one another from the nucleus, and these interactions shift the energy levels in ways that become very difficult to calculate exactly. The result is that heavier elements tend to have far more spectral lines than lighter ones. Iron, for example, produces thousands of spectral lines across the visible and ultraviolet spectrum, a dense and intricate pattern that reflects the extraordinary complexity of its 26-electron structure. This complexity is not a problem. It is, in a way, a gift, because it means that the spectral fingerprint of a complex element is even more distinctive, even more unmistakable than that of a simple one. There is no other element in the universe that produces iron's particular pattern of thousands of lines. No mixture, no compound, no combination of other elements produces exactly that pattern. The fingerprint is unique, and it is indelible, and it is written in light that can travel across the entire observable universe without losing its character. Every color you have ever seen, in a flame or a firework or a glowing lamp, is the record of an electron descending a staircase. Different staircases, different steps, different colors. Different staircases, different colors. And each one has its own staircase, and each staircase has its own music. There is something quietly remarkable about the fact that a human being, standing on the surface of the earth, can know what a star is made of. The sun is about 150 million kilometers away. No probe has ever gone near it. No sample has ever been collected from it. And yet we know with considerable precision that the sun is roughly 73% hydrogen and 25% helium by mass, with iron, oxygen, neon, nitrogen, silicon, magnesium, sulfur, and carbon making up most of the remainder. We know the temperature of its surface, around 5,500 degrees Celsius, and the temperature of its corona, its outer atmosphere, which is inexplicably hotter still, reaching millions of degrees. We know how fast parts of it are rotating, and in what direction, and how its composition changes with depth. We know all of this because the sun, like everything that glows, tells us what it is made of in the language of light. When Kirchhoff realized that Fraunhofer's dark lines were absorption lines, wavelengths swallowed by elements in the sun's cooler outer atmosphere, the implications were immediate and vast. Every dark line was a signature. Every gap in the solar spectrum corresponded to a known element's spectral fingerprint. By matching the positions of those dark lines to the emission spectra of elements measured in the laboratory, astronomers could read off the sun's composition directly, the way you might identify a voice by its particular timbre and cadence, even before you understand the words. But one line refused to be matched. During the total solar eclipse of August 1868, astronomers around the world pointed their spectroscopes at the sun's corona, the pale outer atmosphere visible only when the moon's disk blocked the brilliant face of the sun. A French astronomer named Jules Janssen, observing from Guntur in India, noticed a bright yellow emission line in the corona's spectrum that sat very close to sodium's yellow lines, but was not quite in the same position. It didn't match sodium. It didn't match any element then known. An English astronomer named Norman Pogson had made a similar observation from Madras, and independently, back in England, Joseph Norman Lockyer, who had not been able to travel to see the eclipse but was analyzing the spectroscopic data, identified the same anomalous yellow line and concluded that it must belong to an element not yet discovered on Earth. He named it helium, after Helios, the Greek personification of the sun. The name was a declaration. This element was so far known only in the sun. It took 27 years for helium to be found on Earth. In 1895, the Scottish chemist William Ramsay was experimenting with a uranium-bearing mineral called cleveite, treating it with acid to release the gases trapped within. When he examined the released gas spectroscopically, there was the yellow line, the same wavelength, the same precise position. Helium existed on Earth after all, locked inside certain minerals produced by the radioactive decay of heavy elements. But it had been discovered in a star from a distance of 150 million kilometers by the color of its light alone. This is the kind of thing that is worth sitting with for a moment. An element was known to exist 27 years before anyone held a sample of it. It was known by a single spectral line, a single wavelength of yellow light emitted by electrons in a gas at the edge of a star. The universe had, in its patient way, been announcing the existence of helium in every sunrise and every solar observation for as long as there had been instruments to see it. It just took a while for anyone to hear. The same technique, extended and refined, allows modern astronomers to read the chemistry of objects billions of light years away. The light from a distant galaxy takes billions of years to reach us, but it arrives carrying the spectral fingerprints of whatever it passed through and wherever it was emitted. Astronomers can identify the elements in the atmospheres of planets orbiting other stars, in the clouds of gas between galaxies, in the remnants of stars that exploded before our sun was formed. There is another dimension to this reading of starlight. When a light source is moving toward you, the waves of light it emits are compressed slightly, they arrive more frequently, and the wavelengths appear shorter, shifted toward the blue end of the spectrum. When a source is moving away, the waves are stretched and the wavelengths appear longer, shifted toward the red. This is called the Doppler effect, and it works for light just as it works for sound. The rising pitch of a siren approaching you, the falling pitch as it passes. By measuring how much the spectral lines of a distant star are shifted from where they should be, astronomers can calculate how fast the star is moving toward or away from us and in which direction. It was this technique, applied to distant galaxies in the 1920s, that led to the discovery that the universe is expanding, that almost all galaxies are moving away from us, their light redshifted by their recession, and the farther away they are, the faster they recede. The expanding universe was not found by any new kind of telescope. It was found by looking at the spectral lines of galaxies and noticing that the fingerprints of hydrogen and calcium and iron were shifted uniformly toward longer wavelengths. The universe's expansion was written in the colors of light from falling electrons, measured in a laboratory on Earth. All of this from a single beam of sunlight through a prism in a darkened room. Somewhere outside, if you were to look, there are lights, street lamps, shop signs, the glow of a city against low cloud, the steady red of a traffic signal. We are so accustomed to artificial light that it has become invisible, the way the hum of a refrigerator becomes invisible, simply part of the texture of the world. But every one of those lights is running on the same physics we've been following. Electrons being given energy and releasing it as photons, each one a specific color determined by the specific energy gap involved. Let's begin with neon. The neon sign is one of the most recognizable objects of the 20th century. That warm red-orange glow that hangs in the windows of diners and bars, the script letters spelling out words in curved glass tubing. Neon signs were developed in the early 1900s, and they work on a principle that is almost comically simple once you understand what's happening inside. A neon sign is a sealed glass tube from which almost all the air has been removed and replaced with a small amount of neon gas at low pressure. At each end of the tube is a metal electrode. When the sign is switched on, a high voltage is applied across these electrodes, and this voltage drives electrons through the gas, knocking into neon atoms, colliding with them, transferring energy. Each collision excites the neon atoms. Their electrons absorb the collision energy and jump to higher energy levels. Then, as always, they fall back, and as they fall, they release photons. The color of those photons is determined by the energy gaps in neon's electron structure, and neon's particular staircase produces photons concentrated in the red and orange wavelengths around 600 to 700 nanometers. That characteristic warm glow is not a dye, not a coating, not a filter. It is the light of neon electrons falling back to their ground states, over and over, thousands of times a second in every cubic centimeter of gas in the tube. Other gases produce other colors. Argon gas in a tube glows a pale blue-violet. Krypton gives a whitish light. Mercury vapor gives a blue-green. What we casually call neon signs are often not neon at all. They are tubes filled with various gases, each chosen for its spectral output, sometimes combined with a colored glass tube to shift the apparent color further. The red-orange of true neon is distinctive and unmistakable, but the broader family of gas discharge signs draws on the entire palette of element spectral fingerprints. Fluorescent lighting works on a variation of this principle with an added step. A fluorescent tube contains mercury vapor at low pressure, and when an electric current is passed through it, the mercury atoms are excited and emit photons. But mercury's most prominent emissions in a gas discharge tube are in the ultraviolet, wavelengths shorter than about 380 nanometers, too short for human eyes to detect. If a fluorescent tube was simply filled with mercury vapor and switched on, it would glow with invisible ultraviolet light and appear almost dark. The solution is elegant. The inner surface of the tube is coated with a substance called a phosphor, a material that absorbs high-energy ultraviolet photons and re-emits the energy as lower-energy visible light. This process, where a material absorbs one wavelength and emits another, is called fluorescence, and it is what gives fluorescent lamps their name. The phosphor coating can be tuned to emit light across a broad range of visible wavelengths, producing something that approximates white light. Different phosphor mixtures produce different color temperatures: the cool bluish white of an office ceiling, the warmer white of a domestic lamp. And this is entirely a matter of which phosphors are used and in what proportions. So, in a fluorescent tube, there are two electron transitions happening in sequence. First, mercury electrons are excited by the electric current and fall back, emitting ultraviolet photons. Those ultraviolet photons are then absorbed by the phosphor, exciting its own electrons, which fall back and emit visible light. A two-stage relay race, from electrical energy to ultraviolet to visible light, all in the time it takes to flip a switch. The LED, the light-emitting diode, works on a different principle altogether, one that doesn't involve a gas or a heated filament, but instead uses the properties of solid semiconductor materials. A semiconductor is a material that sits between a conductor, which allows electricity to flow freely, and an insulator, which doesn't allow it to flow at all. In a semiconductor, electrons can move through the material, but only under certain conditions and only within certain energy ranges. In an LED, two different types of semiconductor are joined together at what is called a junction. One type has been prepared so that it has an excess of electrons, more electrons than the neutral material would naturally have. The other type has been prepared so that it has a deficit of electrons. It has what are called holes, places where an electron could sit but currently doesn't. When a voltage is applied across the junction, electrons from the electron-rich side drift across to the hole-rich side and fall into the waiting holes. This process, an electron falling into a hole, releases energy. The size of the energy released depends on what is called the band gap of the semiconductor material, the energy difference between the level where the electron was sitting and the level of the hole it falls into, and the energy released is emitted as a photon. The wavelength of that photon, its color, is determined precisely by the size of the band gap. Different semiconductor materials have different band gaps. Gallium arsenide, used in early LEDs, has a band gap that produces photons in the infrared, invisible to the eye. Gallium phosphide produces red or green light, depending on exactly how it is prepared. Gallium nitride, which was the key to the development of blue LEDs in the 1990s, a development for which its inventors received the Nobel Prize in Physics in 2014, has a larger band gap that produces blue light around 450 to 470 nanometers. The development of a reliable blue LED was a milestone because it finally allowed the creation of white LED lighting. White light requires a broad spectrum, and the simplest way to achieve it with LEDs is to combine a blue LED with a yellow phosphor coating. The blue light excites the phosphor, which re-emits across the yellow and green part of the spectrum, and the combination of blue and yellow-green approximates white to the human eye. More sophisticated white LEDs use multiple phosphors or combine red, green, and blue LEDs in close proximity, mixing their light to produce white. The LED in your bedside lamp, if it is a modern one, is the product of decades of engineering aimed at controlling electron transitions in semiconductor materials with extraordinary precision. The color of its light, its warmth or coolness, its particular quality, is the result of deliberate choices about which materials to use, how thick to make the junction, which phosphors to add, light engineered at the level of electron energy gaps, tuned to comfort and calm. The same physics that Kirchhoff and Bunsen used to discover cesium is the physics that lights your room tonight. Everything we have followed tonight, Newton's prism, Fraunhofer's dark lines, the spectroscope in Heidelberg, the staircase inside the atom, the firework bursting red with strontium, the helium line in the solar corona, the neon tube glowing orange in a diner window, all of it leads back to the same small event. An electron sitting on a higher rung than it needs to be on, falling one step down, or 2 steps, or 3. The gap between where it was and where it lands, expressed as a photon of light released into the world. It is such a small thing. An electron has almost no mass. It is about 1,800 times lighter than a proton, which is itself extraordinarily small. A photon of visible light has no mass at all. The transaction between them, the release of one photon as an electron descends one energy level, happens in a time so brief that ordinary language has no word for it. And yet, this is the mechanism behind almost every color in the visible universe. Think for a moment about the aurora borealis. On certain nights, at high latitudes, in Norway, in Iceland, in Alaska, in the far north of Canada, the sky begins to glow. It starts as a faint shimmer near the horizon, a pale green suggestion, and then it builds and shifts and ripples across the sky like a vast, slow curtain of light. Sometimes it is purely green. Sometimes, on particularly active nights, there are reds above the green, and blues and purples lower down, and the whole sky is painted in moving, breathing color. This is what is happening. The sun, in addition to light, constantly emits a stream of charged particles, mostly electrons and protons. that flows outward in all directions at hundreds of kilometers per second. Most of the time, Earth's but near the poles, the magnetic field lines converge and dip down toward the surface, and the particles can follow them down into the upper atmosphere, entering at altitudes of about 100 to 300 kilometers, where the air is thin but not absent. There, the incoming particles collide with the atoms and molecules of the atmosphere, mostly oxygen and nitrogen. Each collision transfers energy. The oxygen and nitrogen atoms are excited, their electrons are knocked to higher energy levels, and then, as always, those electrons fall back. The green of the aurora, the most common color, comes from oxygen atoms at altitudes of roughly 100 to 250 kilometers. When an oxygen electron in a particular excited state falls back to a lower level, it releases a photon at a wavelength of 557.7 nanometers, a bright, clear green right in the middle of the visible spectrum where human eyes are most sensitive. This is why the aurora is most often green. Our eyes are built to see that particular wavelength particularly well, and oxygen is particularly abundant at the relevant altitudes, and its most common transition produces precisely that wavelength. The deep red of the aurora, rarer, seen higher in the atmosphere above 250 kilometers, comes from a different oxygen transition, one that takes considerably longer to occur. At those altitudes, the air is so thin that the excited oxygen atoms can hold their energy for several minutes before releasing it, because collisions with other atoms are rare enough that they don't knock the energy away before the transition happens. When the transition finally does occur, the photon emerges at 630 nanometers, a deep, soft red, visible on the most active nights as a crimson arch above the green curtain. The blues and purples of the aurora come from nitrogen, both from nitrogen molecules and from nitrogen ions, atoms that have had one of their electrons stripped away by the energetic solar wind particles. Nitrogen's transitions produce photons in the blue and violet range, around 390 to 440 nanometers, and these appear at lower altitudes, giving the base of some auroral displays a blue or purple tinge. A whole sky painted by falling electrons, hundreds of kilometers above the ground, in air so thin it is barely there. Oxygen and nitrogen electrons are descending their staircases, one step at a time, releasing photons of green and red and blue, and the combined light of millions of these tiny transactions is visible from the ground as something vast and slow and deeply moving, one of the most beautiful things that happens naturally on Earth. The same physics governs a distant star. When astronomers look at a star through a spectroscope, they see the same fingerprints, hydrogen's lines, helium's lines, iron's thousands of lines, because the same electrons in the same elements are making the same transitions, releasing the same photons, whether in a star 10 light years away or in a laboratory on a table in Heidelberg. The universe is, in this sense, extraordinarily consistent. The laws don't change. The energy levels don't shift. Hydrogen in the Andromeda Galaxy, 2.5 million light-years away, has the same spectral fingerprint as hydrogen in a glass tube on Earth. The staircase is the same everywhere. There is something in this that feels, if you sit with it gently, almost like a kind of companionship. The light reaching your eyes from a distant star left that star perhaps thousands of years ago, and it has been traveling through the cold and the dark ever since, carrying in its wavelengths the record of an electron's fall in an atom on the surface of something you will never visit and never touch. And when it reaches your eye, your own atoms absorb it, and the information it carries, the record of that distant fall, becomes part of your experience of the world. We are made of atoms too, of course. Every atom in your body was forged in the interior of a star, hydrogen in the first minutes after the universe began, and everything heavier than hydrogen in the nuclear furnaces of stars that lived and died long before our sun formed. The carbon in your cells, the oxygen in your blood, the iron that makes your blood red, All of it was made in the cores of stars, under conditions of pressure and temperature that are difficult to imagine, and scattered into space when those stars ended. You are, in the most literal and non-metaphorical sense, made of stardust. And the electrons in your atoms are sitting on their own particular rungs, in their own particular staircases, ready to absorb a photon or release one, participating in the same ancient exchange that lights the aurora and colors the firework and writes the composition of distant stars in the language of missing wavelengths. The world, at its smallest and most patient level, is always gently letting go. An electron falls. A photon is born. It travels at the speed of light, outward in all directions, until it strikes something, an eye, a detector, a phosphor coating on the inside of a glass tube, and gives up its energy, and the journey ends. This is happening right now in every glowing thing around you, in the lamp beside your bed if it is on, in the glow of a screen somewhere in the room, in the faint light of a street lamp coming through the curtain, in the stars outside, if the sky is clear, though their light has been traveling for years or centuries or millennia and is only now completing its journey to the window of this particular room on this particular night where you happen to be lying. Every color you have ever seen has this same origin. Every color in a painting, every color in a flower, every color in a sunset, every color in a flame, all of them are records of electrons making their small, unhurried descents, releasing photons of precise and characteristic wavelengths, building up, collectively, into everything that the eye can perceive as color and light and beauty. It is, in the end, a very quiet thing, not explosive, not vast in any violent sense, just small, patient, constant. An electron falls, light is made. The universe, at its most fundamental, is this, tiny acts of release, happening everywhere, all the time, in the heart of every atom of everything. And so we leave it there. Somewhere behind you, the day has already grown distant. The light in the room is doing what it has always done. Electrons falling, photons arriving, colors settling softly on everything they touch. You don't need to hold any of this. Let it drift, the way light drifts through a quiet room after the lamp is turned down. Cus, sleep well.